All right, you ready to go? And so today I thought I would step back, change gears just a little bit because I wanted to talk about some practical aspects of piping systems design for the next two lectures. One is I've mentioned a couple applications. This is a favorite of mine, chilled water systems for providing cooling to buildings and maybe in a campus setting or a large setting where you have a need for cooling in different locations. So basically you have a chiller, and that takes warm water and puts out cold water. So it chills the water that goes through it. And that water, after it goes through it, gets distributed to air handling units, which are basically heat exchangers, where then you warm it up by maybe cooling air in the building, cooling air with the fan system and air system. So how do we deliver it? We have pumps, pipes, valves, fittings. This is all the delivery system. So this is just moving energy from one location to the other. If you haven't seen that or observed that, you can move a lot of energy in a pipeline. Just like hot fluid, cold fluid. It's very, very effective at moving energy. We can also put this in context of winter heating needs, and you have a hot water system. It could be steam or just simply hot water. A lot of systems move away from steam just to have a hot water loop. And so the hot water goes to the same air handling unit, different coils in it, but then heats up the air and provides heating to the building. So pipes, this is how you distribute it, and this is what's two ends of the process. So in the general description, we should consider closed systems and open piping systems. What is the difference? Well, it's whether or not the system's open to the atmosphere or closed to the atmosphere. And one is elevation important. Well, elevation's always important, but when you have a system and you have a pump and you're calculating the power required to the pump, if it's an open system, it's very important because typically the pump pushes some water up and then it sprays it out and then it's collected. So it's always having to overcome an elevation head. It's always having to lift it where it throws it out and then it splashes and collects. So that's pumping power. You don't want to neglect that. But in a closed loop, a closed piping system, there is no elevation head. Yes, it may push it up, but it's also coming down somewhere else in a return pipe. Otherwise, it appears in closed systems that you can neglect the elevation in the calculation. So the basic question is water ever exposed to the air, or the fluid that's being circulated, ever exposed to the air, the atmosphere? If it is exposed, well, that's an open system. If it's not exposed, that's a closed system. Cooling towers. Well, this isn't a good example of an open system. So what we have is you can have a natural draft. These are huge, right? Natural draft cooling towers. Or you can have a mechanical draft. Up here, there's fans. I didn't show it too well. And they draw air in and then throw it out at the top. And on campus, we have no natural draft, large concrete cooling towers. We have a lot of mechanical draft cooling towers. All right. So what happens is you take the water and basically it sprays it in, and the air is being drawn in over from the sides, and the air goes out more moist. What happened? Evaporation. Where did the heat that come from to provide the evaporation? It came from the heat of the liquid. Some of the liquid went away, it vaporized, evaporated, but some of the liquid is collected at the basin. That liquid's collected in the basin, and then it continues on. So you always have makeup water in a cooling tower because that's how it's providing cooling to the water. It's evaporating some of it. There's a couple terms. I think I'm going to define these again. Let me see if, here they are on the next page. So here's an illustration of a cooling tower. why do you want to throw heat? It's throwing heat to the environment, so you're coming out with some fairly warm water. You can ignore that temperature right there. You come up and spray it in, and then you have air discharge, mechanical draft, and you're bringing in air. All right, so you collect it in the basin. Typically, you put the pump way in the basement, if you have it. Put it at the lowest elevation so that it has a nice suction head, high suction head, so that it avoids cavitation in the pump. And then you take and throw that cooler, lower temperature water through a heat exchanger, which is picking up heat from refrigerant that is condensing. So this is the condenser side of the chiller. The refrigerant's condensing, and then that's warming up the water. So the refrigerant comes in maybe saturated vapor and goes out saturated liquid, negligible pressure change, but maybe it's 100 degrees F, 110 degrees F, something like that. So you're going to need this water coming out 90-ish degrees F, and maybe it comes out over here dropped about 10 degrees F or so, and then goes in the loop. Well, there's two metrics of performance: the cooling range. So what is the cooling range for a cooling tower? It's a difference in the temperature between the hot water entering, this would be the hot water coming into the cooling tower, and the cold water exiting. It could be as low as 8 degrees F, 10 degrees. If you have a really good cooling tower, it can be quite large, 15 degrees F. All right. So this is just a typical range of the change in the temperatures for the cooling tower. And then there's another, it's called the approach, the difference between the temperature of the cold water leaving the tower. So this temperature is coming out of the tower. Maybe it's coming out at 86 degrees F. That temperature, the difference between that temperature and the wet bulb temperature of the air that's being drafted in to the cooling tower, the atmospheric air. So this air that's being drafted in, you talk about its dry bulb, you talk about its relative humidity, you can talk about its humidity ratio, you could talk about its wet bulb temperature, you could talk about its dew point temperature. The key temperature is the wet bulb temperature. It's closely related to, the next slide talks about it, the ability for the air to hold water. Okay, so for this illustration, the air is shown to come in at around 78 degrees F wet bulb. That doesn't mean the dry bulb's 78. The dry bulb could be 90 degrees, but the wet bulb's 78. Okay, and it just has an illustration. There's a lot of rules of thumb or calculations. So if you're drawing in so many CFM of air, you need to bring into that cooling tower. This illustration shows 275 CFM of air per ton of cooling that's down in the chiller. All right. The water, you need to flow about 3 GPM, gallons per minute, per ton of cooling in the chiller. And often you have a return of 86, and maybe a supply 10 degrees higher, 96. Here I think that's a lower than 96, but I grabbed it from someplace and just ignore it. Just put a delta T of the water going through that chiller. The condenser part of the chiller is going up by 10 degrees. Hence it goes down by 10 degrees in the cooling tower. And the refrigerant comes out warmer, 100 degrees F, but it's liquid and it's going to go and provide cooling to the water that's going to go not in the cooling tower loop. This is a loop going to the cooling tower. That's an open system. The chilled water loop is closed. So here's just some reminder we've been exposed to in other classes: the dry bulb, relative humidity, and wet bulb. But you see that you can have 90 degree F dry bulb, 60% relative humidity, and it'd be 78 the wet bulb temperature. All right. You can get a lot lower wet bulb temperatures, but as a design engineer, you're always thinking this cooling system has to work on a very hot, very humid day. That's the day it really needs to work. So I thought I would remind you of some characteristics of temperatures and different locations throughout the United States, because cooling something in Houston is a lot different than cooling something in El Paso. And we're kind of in between, thermally as well as physically. So this is just grabbed off of a website, what I thought was pretty good. I just grabbed a snippet of it because they had Texas. They had a number of cities in Texas, so I can easily do the comparison. A number of places out there have these type of things. But here's San Antonio, okay? And so what are they showing us? They're showing us 1%. Well, first of all, it's a temperature, 78 degrees or 77 degrees F. And then they're saying 1% of the year, it's worse than that in San Antonio. 5% of the year, it's worse than 76. And 15% of the year, it's worse than 75. Well, basically, as a design engineer, you don't want the system to work on the 1% of the worst days, right? It's really on an hourly basis. So you have an average hourly basis. I think it's right here. This chart shows, if you can read that, the chart shows the average percent of the time, they're doing June through September, that the wet bulb temperature will equal or exceed the degree Fahrenheit value shown. So you could be monitoring every hour of the year in San Antonio at the airport or standard location, and then you could say these are the number of hours that it exceeded was higher wet bulb than 77. It would be on average over many summers, many years, only 1% of the time, 1% of the hours. This really suggests your summer design for the various cities. So you're going to say, you know what, that's going to be my design. It's really ridiculous to design something for everything, you know. Now, I'm going to show another slide. Let's go to it. Here, this side. This comes from NOAA, so National Oceanic Atmospheric Association, right? They basically do the weather and that. So you could get much detailed information about San Antonio, our latitude, our longitude. This is their averaging period from 1973 to 1996. And this is the elevation, probably at the airport, the average pressure, 29.15 inches of mercury. These are design criteria data used by engineers to say this system needs to work in San Antonio, or I'll go get the information for Houston. I forgot to point that out. If you take a look, what about Houston? It's got a higher wet bulb temperature. It's going to be tougher to provide cooling. That's readily apparent. What city in the state of Texas has the worst, if you're the design engineer of all the lists from Abilene down to Wichita Falls? Galveston. How many people been to Galveston? Hot day. Yeah. Oh boy. What's a really close second? Port Arthur. You know, it's along the coast. Really hot and humid. Corpus is pretty bad. 81. Right up there with Port Arthur. But San Antonio. What about El Paso? Whoa, look at that. Isn't that a big difference? That's a big difference. The cooling towers work really well most of the time in El Paso. Okay, back to more information about San Antonio. So here is a 0.4% occurrence, 1%, 2%. Forget the 10 and 15%. Nobody's going to do anything with that for design purposes. You're either going to probably shoot for that 0.4%. We'll talk about that on the next slide, what that means. So design value for the dry bulb temperature would be that it's going to be outside 98 degrees. This is our design in San Antonio at 0.4% with a mean coincident. Now that word can throw you for a loop, but what do they say? They put it in parentheses, average. So it's the mean average corresponding value of the wet bulb. So the wet bulb can really be high on some cool days. I mean, it's not going to be that high, but it depends on both the dry bulb and how much humidity you have in the air. So it's not just correlated with one of them. So what they do is they get the mean coincident or the average wet bulb associated with that dry bulb at this 0.4%, meaning it can be worse than that 0.4% of the hours in a year. This is NOAA's numbers. ASHRAE has slightly different. Here it is. This is the wet bulb down here. That was the dry bulb and then the coincident wet bulb. But if you just looking at the wet bulb per year, the 0.4% is the 78, with the mean coincident dry bulb of 87. This is what people typically design to. It may sound funny that they're designing to 87 dry bulb, but that's when you really have a bad day to try to throw heat out of the cooling tower, because the wet bulb is really high. Okay. Just a reminder, you can put in that 86 dry bulb with the 77 wet bulb, and it'll come in that day had 67% relative humidity. You can find, if you haven't done it, a lot of these online psychrometric calculators. They're pretty handy. You can download them, put them on your phone, put them on your laptop, etc. Can't use them in exams. Here's another one. I just double checked it. So 86, 77, pretty close on the relative humidity. You can look at dew point, all kinds of humidity ratio. Remember all those calculations with moist air? Thermo 2. Let's ask some questions, allow you to do some calculations. So the first question, so if the design, which is basically saying worst case, we're going to design this system to work, right? Well, it better work if it's providing cooling in the summer on the hot day. So if the design conditions for San Antonio are the 77 degree F wet bulb, and the cooling tower approach temperature is 8 degrees F, what is the expected return water temperature from the cooling tower? Now I'll give you a little time to work on that, and I'll walk around. So who figured it out? This is not right, is it? The wet bulb 77, the approach temperature, what did I do? I typed it wrong. All right, so what's the approach temperature? The approach temperature is the difference between the return of the water going from the cooling tower, so the cooling tower return, minus the temperature wet bulb of the air that's providing the cooling. And so if you're designing for a 77 and you have an 8 degree delta T, you add 8 to 77, 85. So why do I have a 9 degree approach? I don't know. How about the next one? There are 8,760 hours in a year. That's a standard year. 8,760 hours in a year. How many hours will the wet bulb meet or exceed 77 in San Antonio? So you come back here, and this is 78. This is 77. So this is the 77. It's a 1% occurrence. That's right. And then if you said, how many hours of the year will it exceed the 78? That was the 0.4%. And 0.4% is 35 hours. No, they're not all together. It could be 2 hours on this day, 3 hours on that day, 35 hours where it exceeds the 78. Okay, the next question. If the mean annual wet bulb temperature in San Antonio is 61 degrees, so that's a lot lower wet bulb, isn't it? So today, the wet bulb right now, I don't know what it is, but it's low. Okay? So the mean annual is 61 degrees F. The cooling tower approach is 8 degrees. That's the same as what we had up here. is 8-degree approach temperature. Then 50% of the time, the cooling tower return temperature is, what is it going to be 50% of the time? So you're designing to bring it back at 85. But today, it's a lot lower than 85. And why is it lower? Because the wet bulb temperature of the air outside is a lot lower. That water is going to come back a little bit under 70 degrees F. Pump in an open system, remember the classic open system is for a cooling tower loop, has to overcome the physical elevation difference between the discharge at the top, this is where you're going to be discharging at the top, and the intake at the basin. So let's say the pump is right here, but it also has to lift it, that elevation, and spit it out the top. Now let's talk about closed system. The classic example is once I have that water chilled, in the chiller it would be on the evaporator side. That's the second loop going through the chiller. Then it's ready to go distributed throughout the campus, throughout the buildings and that. So this is going to be a closed system. Now here's two systems. Both of them are shown just to have one chiller here, all right, one pump, and they have to go and feed 3 units. You could call these air handling units, you call them heat exchangers, just they have to feed 3 units. So let's see and what is the difference. And I'm going to go around, but I'm going to just walk you through it a little bit. So the water is going to go which way? That way, right? And that way. And then here's another system that has 3 units. One pump, both of them have one pump, not difference in the number of pumps, not difference in the number of chillers, no difference in the number of air handling units, but it's something different. Please describe the difference on your paper, and I'll walk around and see how you describe the difference between these two systems. So let me make a comment. Let's do this. Let's track a chunk of fluid, I'll color-code it blue. It's going to come out, it'll go through the pump, it just has the pressure increase, and then it comes to this, and that's a Y. It could go this way or that way, true? So let's do this. Let's say the blue is going to go this way, and I'm going to trace a purple. I'm going to trace a purple, comes out, and it's going to go straight. So, but where does the blue go? Okay, the blue goes through the first air handler. The purple, I'm going to come down, and I'm going to let it go through the second air handler. Okay, the second terminal, and maybe another color, orange, will come out, and it'll go through the third. True? See what we're doing? Now, finish the path for the blue, finish the path for the purple, finish the path for the orange, and then go down and do it for the next system. Say, hey, I'm going to start the track coming out of the chiller, blue pack of fluid that's going to go through the first air handling unit. Trace it. Then grab a purple, start it from the chiller, go through the second air handler unit. And then grab a different color and then trace it. And then make the observation, okay? Can you make an observation for me then? Thank you. I'll walk around. All right, let me go ahead and clean this up and maybe get a thicker pen, and that'll make it a little easier to see. This one, we're going to trace the blue. It comes out, it goes through this air handler unit. Now, when it comes into the chiller right here, it's going to undergo a delta T of cooling, okay? And guess what? It's going to go a delta T of being warmed there. And unless there's a lot of stray heat transfer, hopefully it's well insulated in the pipes, and there's not a lot of stray heat transfer, so the cooling in the chiller is the same as the warming in the air handler. So it's nothing to do with the temperatures. Because once it goes through that first air handling unit, does it then go to the second air handling unit and then the third? No, it'd already be warm. It needs to get back to the chiller and be chilled, right? So it doesn't go in series through the air handlers. It's really what's going to happen now that it's after. So after, where does it go? Isn't that the route back? Let's do the flow to the first air handler unit in the second system. Comes out cold, goes to the first, is warmed. Hey, what are we doing? Hey, where are we going? Yo-ho, I'm trying to get to El Paso. You're driving me to Houston. Isn't that it? One has a longer path. True? That's one observation. Now you got to make the same observation about the other ones. Okay? Let's take a look. I just don't want to belabor the point, but wasn't this our orange? That's going to go all the way down and then go through this one and then back. True? All right, let's take a look at the orange. Go here. Does the path of the orange look about the same in both of those systems? It does. Does the path of the blue look about the same in both of those systems? No. Which one? What's the big difference between the path of the blue in one and the path of the blue in the other? The length. The length is a lot longer. So, first of all, if you're a pack of fluid, there's 3 packs of fluid and you want to distribute 1/3 here, 1/3 here, 1/3 there, right? You would like it to be naturally balanced so that the same flow, I'm not changing the sizes of the air handlers. This is we need 1/3 to go here, 1/3 to go here, 1/3 to go there. Which systems, not clicker question, don't shout it out, I'm on to walk around. The next question now is what system will more easily deliver balanced flow, 1/3, 1/3, 1/3, to those air handler units? All right, so what we see is now that the top system, the one on the top versus the bottom, okay, the blue is a lot shorter line than the one going through the third air handler, which I sketched as orange, right? This is a lot longer, this is a lot shorter. Naturally, if they are the same diameter pipes in the system, the shorter one has less resistance, the same pressure gain from the pump, more flow is going to go through that first chiller. The flow rate, let's say Q1 going through this first chiller is going to be greater than Q3 of the top system. How about the bottom system? Well, they have about the same length of the pipe. So the flow through this one would be closer in approximation to the flow through that one. This would have typically all of them about the same, right? The same GPM through each of these air handlers. This is more naturally balanced. But how did they do that? Well, they changed how you get the return back to the chiller. Let's take a look at the top one. How would you describe the return? Once it got to the chiller it needed to, how did it get back to the, once it got out of the air handler unit, how did it get back to the chiller? As fast as it could. Let's compare this one on the bottom. Once it came out of the air handler unit, right here, and out of the air handler unit, how did it get back to the chiller? So anyway, here's the terms. Hopefully these terms make sense. It's direct return. It's the shortest return, getting me back to the chiller. That's the design on the top. That's not as balanced naturally. The reverse return, meaning I know that you were the first to get it, but you're the last in the leg, so to speak, on the return. The returns are reversed from the supply. So it's called reverse return. This is more naturally balanced. I think it's conceptually worth more than it is practically because you just put a pump in there and you draw in what you need. You put separate pumps. We saw that in the worked example problem that we did. You put a pump there and a pump there and a pump there, and then if this one really needs a lot of flow, that pump kicks on and pulls it in. But you still have a main supply pump. Typical piping system design process. How do you do it? So let me try and bust it down into steps. First of all, it's for a new system, right? New system. You're just doing it on paper, and then you'll go build it. So you're designing it. You find out how much cooling is needed, and those are what they call the design load calcs. Somebody said, I'm doing some load calcs. It's trying to figure out, I need to have this air handler, and I need 20 tons of cooling in that air handler, or 15 tons. Those are all associated with what's going on in that zone of that building. I've got a lot of people, I've got a lot of machinery, I've got a lot of solar load, glass, I've got poor insulation, or it's an interior space with lots of insulation, not leaking to the outside, whatever. There's a lot of calculations just to do that. So you back that up and say, these are how many tons of refrigeration needed in that zone. Okay. Then you say, well, I've got to provide chilled water to that air handler to provide the cooling to handle that load. So the easy equation that a lot of people use is I say 500 times the delta T of the water times the GPM of the water, that gives me so many BTUs per hour of cooling. So what's DT? The temperature change of the chilled water in the air handler unit. It could be a few degrees, it could be a lot of degrees. It's matching what's going on in the chiller. And the greater the delta T, the better it operates, just economically, because if the delta T goes up, DT goes up, what about the flow rate, the GPM, for the same cooling? It can go down. You don't have to circulate a lot of water. But if you have a low delta T, man, you got to throw more water in the loop. Okay, so those are the terms. What's the 500? Well, delta T in degrees F, gallons per minute. Multiply by 500, you get BTUs per hour. And what's a BTU per hour? 12,000 BTUs per hour is 1 ton of refrigeration. 1 ton. A lot of times they'll use this MBH. Okay, the BH is BTUs per hour. What's the M? They got rid of the Roman numerals for the Super Bowl 50. I think isn't it now? Super Bowl 50 this week or something? And it's no more Roman numerals, right? Did you notice that? Yeah, they got rid of it. It's like my wife looked at that and said, hey, what did they just do? What's all these X's and V's and I's are gone? Come on now. Anyway, I think that goes back to, and I may be wrong because I can't remember my Roman numerals, but it's 1,000 BTUs per hour. Now, there's a few people that'll say M BTU per hour, and they'll say, oh, that's 1 million. So be careful. You could easily be 1,000 off. It's not like M means the M to everybody. Okay, just be careful. But the vast majority, that M is 1,000. All right, so there you go, a little review. So you determine the GPM flow rate. Now, here's the question. Determine the GPM flow rate for a cooling load of 10 tons, and you have a 10 degree F temperature change across the air handler unit. I pause, and I want you to make that calc. So pressing forward, how many people got 24-ish? 24 GPM. So that's how my flow rate of water. So let's keep on. So in a reminder, somebody had to do the load calcs to say this is how much cooling I need on a very bad day in this building, in this city, blah, blah, blah. I need the flow rate. I get the flow rate of water because I have a certain delta T that I'm designing around. I need that flow rate. You then lay out the pipe. You say, I'm going to have to turn here, turn there. I'm going to this building over here. I'm getting to the 3rd floor. You got to calculate all those lengths. Because it's a closed system, you can almost neglect the elevation. But if you really wanted to know what is the pressure in that pipe at that location, at that floor, you would need to know the elevation because it's always hydrostatic head. But the pipe takes it up, the pipe takes it down. In the net, it's not like splashing it up like an open system. Now, once you have the layout and you have the lengths, you really need to select the pipe. Is it going to be steel? Probably. Is it going to be copper tube? Probably. Is it going to be some plastic, PVC or CPVC? CPVC can handle the temperature. PVC is just traditional water, cold water supply. Those are the main 3. We're not putting a lot of concrete. I know that we have that in our textbook. We get concrete, push it through concrete pipes. But so you need to select the type, and then you need to select the diameter. Well, ASHRAE, here's some suggestions. Says the velocity limit should be 4 foot per second. Don't go faster than that if it's a small 2-inch or smaller pipe. This is a rule of thumb, heuristic. Why? Noise. Noise. It's going to make noise. You're going to hear it rushing. The other is, if it's a larger pipe, then ASHRAE suggests you don't want a pressure drop of 4 foot per 100 foot of length. 4 foot elevation head loss per 100 foot of length. That just comes from a lot of experience. So this is energy per weight per 100 foot of pipe length. This is what that term is. Maybe the first time you look at it, you say, what, 4 foot per 100 foot of what? That's a head loss for larger pipe. Also, the water velocities shouldn't be too slow either. If they're too low, what's going to happen? You always have air dissolved in water. And when you heat it up, it will come out. If it's cold water, it can absorb a lot of air, right? That's why fish love oxygen. They get oxygen out of the water when they're through their gills and they're swimming around, and they like cold lake water. They go to the bottom of the lake and hang out in the hot summer days because they can breathe easier. And at night when the cooling occurs, they like to come up, and they will be at the top when the water's cool up there. So water and air mix, so to speak, and you will get some air come out of the system and you in the middle of your system. And so typically when it gets warm and low pressure, air comes out. You need to get that air to a location and then get it out of the system. So you need to sweep and then train that air along with the flowing water. So you need to keep it at least this fast so that you can collect it and then get it out of the system somewhere else. So here are some design criteria. True? All right. Once you've selected your pipe, type of pipe and diameter, you know its length, you know the layout, you have all the fittings. Well, you can just use a rule of thumb on the fittings, or you can do the actual summing them up. And with a computer program, sum them up. You got to do something fast, multiply by 1.5. Who knows how close that is? But so here's a thing. I say I have 4,000 foot of physical length of pipe. What is the equivalent length that I can use as a scoping calculation? You finally got a correct answer. I knew I would keep working on you. That was a low blow, wasn't it? Well, there's a lot of software out there, and so what I thought I would do is say, hey, let's just expose you to some of the software. You can go, this is Bell and Gossett software. You can download it, and then you can play with it. Now it's up and running on this system. So, number of different things to look at. I can input some sort of temperature. I was playing with the 38 and 48 water, right? The water's changing between 38 and 48, 10 degree delta T. It's going to be chilled back to 38, come out of the chiller, go up to 48 out of the air handler unit. I put in my gallons per minute flow rate. No, actually the load. I put in the load. I think if I get rid of this, and then 38, 48, and then how many mega BTUs? I had how many tons? I forgot. It was 10 ton. 120, and oops, too many. And you can see it's already doing the calc. So it's 24 GPM, just what our hand calculations showed. And then you come over here, here's a reminding you 10 tons, and this is how many GPM of flow per ton. This is how many BTUs per hour. This is how many kilowatts. There's a lot of helpful, so that you don't feel. And then there's a little footnote, watch out for units. MBH may be interpreted one way or the other. Skip the CV. Let's go to the flow and the pressure drop. So I could select steel, copper, PVC, plastic. So let's go with steel, and let's go with, 4-inch. Well, if you go with 4-inch, what is the friction loss? It's pretty low, 0.05 foot per 100. That's great. The velocity is a little low, isn't it? 0.6 foot per second. It's not very fast flow through the system. It's probably too big for this GPM. So we drop back and we change it to 2-inch. Oh man, why didn't you show us this the first day? Anyway, they want to sell you stuff. So they're in the business of making engineers' life easy so that you can select their material, and so they may put these out to help you do a good job. So let's see what else is of they show you the Reynolds number, the relative roughness. Let's say I change it to copper. You can see the relative roughness goes way down, doesn't it? Type of flow, it's transitional flow. Think about that Moody diagram. It's not fully developed. It's definitely not laminar. It's where it's a function of friction factor and Reynolds number. There's the friction factor, feet per second, 2.5, etc. That's pretty good, foot per second. This would be a good choice. I think if you went with 1.5 inch, you're getting a little high on the friction in that. So typically you go a little higher. There you go. So let me jump back here. I see I'm running out of time, or getting close. So we can then input into this software the length, so the pressure drop and the length. So I put in 6,000, I could put in 8,000. Whoops, that's too many feet, isn't it? 8,000, or what is that, 80,000? Just put in 6,000. And you get the friction loss, 1.44 foot head per 100 foot length. And this is the total head loss. And it's doing the calculations for us. Let me come back. I think this one right here. I don't know why they have it over here. They have the annual energy costs. We're going to now make those calculations. Let's go back here. So you did the load calcs, you did the flow rates, you did the layout, you had pipe diameter and the type of pipe. You put in the fittings, or you estimated the equivalent length to account for the fittings. Now you calculate the head loss. So what is the head loss of that 2-inch diameter steel pipe with 24 GPM? Well, I didn't want to do that calc, so I relied on the software. So the head loss was about 125 per 100 foot of length. We had 6,000 foot of length, hence 75 foot of head loss, energy per unit weight, or equivalent energy per unit mass, 75 foot-pound force per pound mass. So 75. Let's go back to the thing. And didn't we get a total head loss of, what did I do wrong? Is it 6,000? 1.4. Did I change the diameter? Oh, I think I changed the pipe. Put steel. Steel, okay, 75 foot. Right? Okay. Why was it less in the copper? Because it's smoother. So with that 75, then you can say size the motor and the pump. So the pump needs to basically provide that amount of head. I didn't account for how much head loss is in the air handler or the head loss that's in the chiller to push it through. Just so we're just doing this. But you find that the fluid power, the flow rate, blah, 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 you get so many horsepower, almost a half a horsepower in the fluid power. The efficiency of the pump's 80%, hence the motor efficiency is 0.6, almost 0.6 horsepower. And they're doing those calcs for you right in this vicinity. Okay? And then you can actually do, if you know the cost of electricity, they actually 10 cents a kilowatt hour. There's your annual cost, $371 just to push it through the pipe. All right. Well, with that, I didn't get as far as I wanted to, but we're done for today. Thank you for your attention.